Welcome back, everyone. I'm Akash Joshi. I'm the OR Guru, and today we're going to be discussing Gaussian elimination. This is the second part of a two-part series. Please check out the Gaussian elimination part 1 video that I posted. Um, and yeah, you'll need that video to understand the concepts that I explain in this video. In this video, we will be discussing the row exchange method, Gaussian elimination's complexity, and what to do in a case of a singularity. Okay, first let's talk about the row exchange method. We are going to conduct this process if a 0 appears at a pivot position. If you need a reminder, a pivot position is the position right here, here, and here once you get the system of equations in a triangular pattern. So just look at this system over here really quickly. Don't pay attention to how we got there for now. This system over here, the pivot positions would be 10, 25, and -15. In a triangle shape, you would take the leading coefficient and call that the first pivot, the second pivot, and the third pivot. Okay, so what do we do if a 0 appears in the pivot position? Okay, let's look at an example. So here is our system of equations. Pretend like there's a number there. It can be any number. For the purpose of this example, we won't use a number, and you'll understand later why I didn't use a number. Um, so we get -15z first because we multiply this first equation by 2 and we subtract them from one another. So 20x plus 10y plus 10z, if we subtract that from 20x plus 10y minus 5z, we're left over with -15z. And if you notice, um like I explained in the last video, we need, if there are three equations, we need three variables over here, two variables over here, and one variable over here. If you notice, this is kind of switched up because there are three variables here, one variable here, and two variables here, and this makes our pivot position over here a 0. So what do we do if a 0 appears in this pivot position? We would simply just flip the second row and the third row around, and that way we don't have a 0 in a pivot position anymore. We have a 10, a 25, and a -15 in the pivot positions. And we can only conduct the row exchange method in non-singular cases. Non-singular cases are systems of equations in which there's only one solution. If there is ever a scenario when there are multiple solutions or zero solutions, we have something known as a singularity. The system of equations is then known to be singular. Here we have a system of equations and we are going to determine if it is singular or not. So the way we would do that is we would try to eliminate the first variable in these bottom two rows as usual. We would multiply this one by 2 and subtract them from each other, and we would be left over with -15z, and this variable also happens to be eliminated. And over here, we would just add this third equation and this first equation, and we would get 15z, and it just happens to be that this variable is eliminated as well. So let's see if there are infinite solutions or no solutions. Since we can't really do a row exchange because there are still only one variable in two equations, we know that this solution is going to be singular. If this row had two variables left, then we could just perform a row exchange and the system equations would not be singular. It would be non-singular. Okay, so let's look at some scenarios here. If -15z was equal to 30 and 15z was equal to -30, then there would be infinitely many solutions, because even though there might only be one z solution, there would be a lot of other solutions for the x and y. If -15z equals -30 and 15z equals 30, there would also be infinite solutions. And once there are infinite solutions, we call the system of equations to be consistent. So if -15z is equal to a number and 15z is equal to a totally different number, there is no solution to the system of equations, and we call the system of equations inconsistent. Keep in mind that both of these scenarios are still singular. The way we define singularity is if there are no solution or infinite solution, and here there are infinite solution and no solution. Let me just clarify here. It doesn't have to be infinite solution. It can also be multiple solution. But a more precise way to look for singularity is if there isn't a triangular structure to your system of equations by the time you're finished performing stage one or step one of Gaussian elimination. And yeah, okay, let's talk about Gaussian elimination's complexity now. So, what is the computation time of Gaussian elimination? Well, assuming that n is the number of rows or variables in your system of equations, we are going to call the computation time of Gaussian elimination big O of n cubed. Big O is is a statistical measurement of the computational time of an algorithm. And yeah, so this is the computation time for Gaussian elimination is proportional to n cubed. So if we were to draw a graph, time time would be on the y-axis and n would be on the x-axis, and we would have an n cubed graph here. Okay, so when n is large, very large, like for example a million, the number of operations necessary to perform the Gaussian elimination is n cubed divided by 3. It's approximately n cubed divided by 3. Based on the system of equations, that number will change, but it's a pretty good indicator of how many operations your computer will have to perform when you are programming it to perform Gaussian elimination. Okay, that is it for the Gaussian elimination complexity. These two terms pretty much define its complexity, and it gives you a good idea about Gaussian elimination's uses and purposes. So yeah, thank you for watching. I'll see you next time. Goodbye.